Hi, I'm Orlandi and I'm pleased to show you our work, which is about the monitoring of Sentinel-1 data through the InSAR technique in order to understand more about the earthquake that happened in Durre city in 2019. So we can see quickly the area, which is about the epicenter was the magnitude of the event was 6.2 and the epicenter is more or less 20 kilometers by Durre, but actually the earthquake was felt also 400 kilometers far from Durre. It happened during the night of 26 November of 2019 and it also was strong and it can be compared to the very highest and strongest ever recorded earthquake that happened in 1971 in Montenegro. So in this study we want to make advantage of the InSAR technique in order to understand more the parameters of the fault that created this earthquake, because there are some discrepancies between the dips and strike and depth calculated in previous studies. So we will do interferograms and we also propose the decomposition maps, and finally we propose the inversion of the data. So as you can see here, firstly we have the wrapped interferograms that show the phase in radians, so actually both ascending and descending into different periods covering both the earthquake. And we have the phase movement in radians, and the same, obviously the interferograms are wrapped that show the same movement but actually in meters. So as you can see in both the tracks ascending and descending, there's a huge pattern of uplift, and it is also shown by the profiles that where we have a maximum of 10 centimeters in the upper part. So this is also confirmed by the decomposition maps, because actually one of the limits of InSAR is the measurement in the line of sight, so in the direction of the satellite. So in order to have a better estimation of the surface displacement, it's always good to use, for example, ascending and descending, and if there are also GPS, so to have a more clear perception of the surface displacement. So as you can see here, it's also confirmed that the movement was mainly vertical. Finally, we show also the modeling of the data, and as you can see here, for example, for the ascending track, we have a good correlation between the observed, the model, and the residual. So, for example, the first one is wrapped and the second is unwrapped, and as you can see, is almost zero. And the same also happens to the descending track, where we have a good correlation between the observed, the residual, which is almost zero. So finally, here I reported the parameters of the fault that we agree to be around strike 337 and around 21 for deep and almost 17.8 for the depth. So as you can see in these images, there's the plane of the fault, that it's a fault that dips 21 degrees to the east. So as our conclusion, we can say that the surface displacement plus the inversion of data is a good way, and it's a good comparison to understand and better retrieve the deformation source. The fault that causing this earthquake is dips in a low angle to the east, about 21 degrees, and it's also according to the area, because actually this is a very active area tectonically speaking, because it's the place where collision between two plates occurs. So as you can see, there's also a good trend between the fault proposed and also the other thrust shown in these images. Obviously, further studies may imply also the GPS as a third component to better estimate the surface displacement. Thank you very much for your attention.